I will be discussing the physical properties of materials. And the physical properties are important when it comes to manufacturing as well. And that's the reason we're covering them here. Properties that define the behavior of materials in response to physical events other than mechanical forces. So those will include volumetric, thermal, electrical, and electrochemical properties. Components in a product must do more than simply withstand mechanical stresses. So there's a lot of cases that we use materials to, for example, conduct electricity or prevent conduction. We may need materials to allow heat transfer to occur or allow it to escape. We may need materials that transmit light or block transmission. So a lot of components are not designed to just take mechanical loads, but also be able to perform certain functions apart from mechanical stresses. So these physical properties in manufacturing are important because they often influence the process performance. Examples are in machining, thermal properties of the work material determine the cutting temperature. You don't want the cutting temperature to damage the material, right? So also in machining, thermal properties can affect the tool life. For example, in microelectronics, electrical properties of silicon and how these properties can be altered by chemical and physical processes is the basis of semiconductor manufacturing. So let's continue to microelectronics, right? The electrical properties of silicon and how these properties can be altered by chemical and physical process are the basis of how semiconductor designs work in manufacturing. So these two areas are examples of the importance of physical properties in manufacturing processes. So then we have volumetric and melting properties, for example. In these cases, properties are related to the volume of solids and how the properties are affected by temperature. That includes density, thermal expansion, and melting point. So why is density important? Is because is an important consideration in material selection for a given application, but it's generally not the only property of interest. Strength is also important. So the two properties people look at is strength to weight ratio, which tells you how structurally efficient something is. A part is compared to its density, and which is the tensile strength divided by density. So that's really what that definition is. This is a useful ratio in comparing different materials across a range of applications and a range of materials. In the case of thermal expansion, density of a material tends to be a function of temperature. In general, density will decrease with increasing temperature. Volume per unit weight increases with increasing temperature, and so thermal expansion is the name for this effect of temperature on density. We measure that by the coefficient of thermal expansion alpha. And the thermal expansion matters in a lot of different manufacturing processes. For example, if you have a metal bonded to a composite, the difference in coefficient of thermal expansion as it go through higher temperatures or cold temperatures can cause a residual stress or thermal stress induced by the mismatch in the various coefficient of thermal expansions of the various respective materials. And that can cause stress, that can cause cracking. And so that's why understanding thermal expansion is important in a manufacturing process. Also, thermal expansion is important for creating tight fit connections and things like that. Here's an example of what I mean with that. So you have a thermal expansion manufacturing. So thermal expansion can be used in shrink fit and expansion fit assemblies like this, where you're trying to develop an interference fit for the required application. What we do there is the part is heated to increase the size or cooled to decrease size, and that permits insertion into another part. And when it returns to the normal temperature, then you have a great tight fit connection. When part returns to ambient temperature, you get that tight fit assembly you wanted. Thermal expansion can also be a problem in heat treatment and welding due to those thermal stresses, and also the example I gave on the adhesive used to bond a composite to a metal, for example. So let's look at the melting characteristics of materials. So here in the y-axis, I have the specific volume, which is 1 over density, and in the x-axis, I have temperature. And so the changes in volume per unit weight, we call 1 over density there, and that's as a function of temperature for, say, a hypothetical pure metal, alloy, or glass, right? So here's your pure metal, here's your alloy here, and here's your glass. So if I take glass, for example, at the glass transition temperature, you will see a change in the density of the material as I go to liquid, for example. For a solid alloy, I will again go through a solidus region, and then I'll have a mixture of liquid and solid alloy until I then reach liquid. And then for a solid pure metal, however, if I have a solid pure metal, when I transverse the melting point, then it will become liquid. So you can see that the specific volume and temperature for the various materials, the response is quite similar, but it's different, and it depends on the kind of materials we're talking about. So those melting characteristics are very important in the manufacturing processes. So the melting of non-crystalline materials is different. So this is looking at glass, solid alloy, and solid pure metal, but now looking more carefully at the non-crystalline materials like glass, so in this case glass, there's a gradual transition in this case from solid to liquid. That's not obvious. So for example, for solid pure metal, I go from solid to melt, and then I go through melting point and suddenly I get liquid. That behavior is different from glass. The solid material will gradually soften as the temperature increases. Typically that happens at the glass transition temperature. And so as the solid material gradually softens as the temperature increases, finally becomes liquid at the melting point. However, during softening, the material has a consistency of increasing plasticity as it gets closer to melting point. As you have more plasticity, it becomes more like a fluid. The melting of metal alloys, which is the red line here, unlike pure metal, most alloys do not have a single melting point because now you have two more than one metal and your alloys now. Instead, the melting begins at a temperature called solidus and continues as temperature increases. So here is a solidus, and it continues as the temperature increases until converting completely to liquid. And that temperature is called, at the temperature when that happens, is called liquidus. Between the two temperatures, the liquidus and solidus, those two temperatures, the alloy is a mixture of solid and molten metals. The exception is a eutectic alloys melt at a single temperature. We'll talk about it. So let me focus now. Let's talk about this example here. So that's an example for a solid alloy, right? In this case, I have lead and tin. So lead is Pb, and then tin is here Sn. So as I go from lead to tin, so that's the percentage of tin I may have in the alloy. So here Sn, I have 100% tin, and then here I have 100% lead. So 0% tin in this case. And so then that's what the x-axis is. It tells you the percentage composition of tin. And the reason there's a great example, lead and tin, is because this is used in soldering. In the y-axis, I have temperature, right? And so let's talk about the different regions. When we have less tin, so mostly lead, at these temperatures that you see here, you have a solid state called alpha. And that state is going to be mostly lead. Likewise, when I look here on the right where it says beta here, this little triangle here, at these particular temperatures, the behavior is going to be mostly driven by the tin. In these temperatures, this region. When I look at this region here, this region that looks like a trapezoid, this curve here, this enclosed region here, the behavior at these temperatures below 183 degrees C, these temperatures here, is going to be a mixture of tin and lead with the composition driven by this x-axis. Then here, there's an interesting point here called the eutectic composition. At this point, at this particular composition, 61.9%, at this particular temperature of 183 C, you can see here that the behavior can go from a mixture of solid that has tin and lead, it can go from solid to liquid suddenly through this point. And so that's what I meant with there's certain alloys that have a eutectic point where you can go from solid to liquid suddenly. And that happens at this particular point here, that composition. When I look at these temperatures and for particular compositions, you do get a zone of liquid here. So if I have a composition of 20%, this particular temperature is very likely going to be a liquid state. So that's how these diagrams are used. This is called a phase diagram. Now I look at, say, a composition of 20% and about, say 250 degrees. So you're looking at solid lead suspended on the liquid that's mostly tin. And so then the beta plus alpha will be solid tin suspended in a liquid that is going to have lead. So these are these phase diagrams are used, but this is just showing you that transition that we talked about from solid and liquid, and then to liquid. And then, but there is an eutectic point where you could have that jump from solid to liquid. I hope that was clear. Now, why is that important? The importance of melting in manufacturing is that metal casting, the metal is melted and then poured into a mold cavity. The metals with lower melting points are generally easier to cast. And so understanding these phase diagrams becomes very important, particularly when you have alloys. Plastic molding, you're going to have melting characteristics of polymers. And that's important in nearly all polymer shaping processes, understanding those melting characteristics. Then the third one here is sintering of powder metals. Sintering does not melt the material, but temperatures must approach the melting point in order to achieve the required bonding of powders. Now, looking at thermal properties, the thermal expansion, the melting, and the heat fusion are thermal properties because the temperature determines the thermal energy level of the atoms, leading to the changes in the materials. Additional thermal properties that we could discuss are specific heat, the thermal conductivity, and these properties relate to the storage and flow of heat within a substance. And all these properties can become extremely important in the manufacturing processes. So thermal properties in manufacturing is important because heat generation is common in so many processes. In some cases, heat is energy that accomplishes the process. For example, heat treating, sintering of powder metals and ceramics. In other cases, you may have heat that's generated as a result of the process. Like cold forming or machining of metals, those are going to generate heat. And understanding how that heat is removed in those processes can be important. Electrical properties very important. Some engineered materials exhibit a great variation in their capability to conduct electricity. You have flow of electrical current involves movement of charge carriers. You have small particles that possess an electrical charge. In solids, these charge carriers are electrons. In a liquid solution, charge carriers are positive and negative ions. So again, in solids positive, in solids, these charge carriers are electrons. In a liquid solution, you have both positive and negative ions. So metals are the best conductors of electricity because they're metallic bonding. Most ceramics and polymers whose electrons are tightly bound by covalent or ionic bonding are poor conductors. Many of these materials are used as insulators, as you will see later in the course. We'll talk about that because they possess high resistivity. Semiconductors. Now, semiconductors are materials whose resistivity lies between insulators and conductors. Most common semiconductors materials is silicon. And that's because they are very abundant in nature. They're so low cost and easy to process. But what makes semiconductors unique is the capacity to significantly alter the conductivities in their surface chemistry into very localized areas to fabricate integrated circuits. You'll learn later that silicon is a very important material in the fabrication of integrated circuits because of the semiconductor property that it has. That of having properties between insulators and conductors. It has both, which is very beneficial. Electrical properties manufacturing can also be used in the advantage of machining. So electric discharge machining uses electrical energy in the form of sparks to remove materials from metals. The important welding processes such as arc welding and resistance spot welding, they also use electrical energy to melt the joint, to be able to melt and join metal. Capacity to alter electrical properties of semiconductor material is the basis for microelectronics manufacturing. So again, very important electrical properties in manufacturing. Then you have the area of electrochemistry. That's a field of science concerned with the relationship between electricity and chemical changes and converting electrical and chemical energy. In a water solution, you can have molecules of an acid base or salt, and they can be disassociated into positive and negative charge ions. Ions are the charge carriers in the solution. So they allow electric current to be conducted, playing the same role that electrons play in a metallic conduction. So you have electrochemical processes. One is electrolyte. That term means ionized solution. You have electrode where current enters and leaves the solution in an electrolytic conduction. And so for both of those, you have anode, positive electrode, and cathode, negative electrode. The whole arrangement is called an electrolytic cell. Okay. So electrolysis is the name given to these chemical changes occurring in the solution. At each electrode, chemical reaction occurs. For example, you can have deposition or dissolution of a material, decomposition of a gas from a solution that can occur. And how we use that in manufacturing processes? Electroplating. That's an operation that adds a very thin coating of one metal to the surface of the second metal. It could be for many purposes. Electrochemical machining is a process in which material is removed, and we do that and use that to be able to machine a part. And then the production of hydrogen and oxygen gases, also very beneficial there. So with that said, I hope you enjoy these lectures and we'll continue learning about manufacturing. Again, these are very introductory course. There'll be some videos to help you understand these materials. You have a beautiful day.